You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Jim Green. Dr. Green has served as NASA's chief scientist since May 2018. Before that, he was the director of the Planetary Science Division at NASA headquarters. Under his leadership, several missions have been successfully executed, including the New Horizons spacecraft flyby of Pluto, the Messenger spacecraft to Mercury, the Juno spacecraft to Jupiter, the Grail spacecraft to the Moon, the Dawn spacecraft to Vesta and Ceres, and the landing of the Curiosity rover on Mars. Dr. Green received his PhD in space physics from the University of Iowa in 1979 and began working in magnetospheric physics branch at NASA's Marshall Space Flight Center in 1980. In 1988, he received the Arthur S. Fleming Award for Outstanding Individual Performance in the federal government and was awarded Japan's Kotani Prize in 1996 in recognition for his international science data management activities. He also recently received the NASA Exceptional Achievement Medal for the New Horizons flyby of the Pluto system.
Jim Green, welcome back to the program.
Well, thank you very much for having me.
Now, Jim, when we last talked on the show, we were musing about the Mars copter and landing of Percy. And now that has happened. It's on the ground and in the air on Mars.
Yes,
and
it is.
I was thinking about this idea of controlled flight on Mars, in Mars's atmosphere, and I was sort of juxtaposing that on human flight. The Wright brothers and before, and the contemporaries, and the balloons, the Civil War era balloons, and before. People had always dreamed of flight in the atmosphere of Earth. Mm-hmm. Yet now, the first time we try it in a completely different atmosphere with a totally different makeup, we have a copter flying around on Mars. And I find that to be utterly historic. Now, and congratulations to everybody at NASA for that. That's
yes, indeed.
Stunning stuff.
Thank you. I will carry the message forward.
Now, your interest includes Civil War era ballooning.
Yes, it does.
What's your view on this? What's your overall historic take on what happened here?
Well, right at the time of the U.S. Civil War, so that's in the 1860s, of course, at the beginning, the newspapers were going crazy about, well, if you want to observe from afar, it's really in the air, and so they were always encouraging the government to hire these balloonists, because that was the top technology of the era, that and the telegraph. Those were those things that indeed really excited the public. And of course, the head aeronaut that will become the first aeronaut for the U.S. government was Thaddeus Lowe. And he did a demonstration on the Mall, which we actually recreated 150 years later, okay, where we actually launched a balloon off the Mall that was tethered with a telegraph operator, and he sent the first telegraph from the atmosphere aloft on a balloon 500 feet to President Lincoln. Lincoln was excited that indeed Lincoln pushed hard to create this first Air Force. Okay. Now, one aside, if I have another minute, would be that once Lowe became chief aeronaut, he hired other aeronauts, and he built 7 government balloons. And one of the aeronauts that he hired was John Steiner, who had a lot of background originating in Germany. He spoke fluent German. And at one time, he actually took Zeppelin, who was visiting from Germany, the U.S. Army. He was working with Hooker, and Zeppelin indeed went up with John Steiner in Minnesota between battles. When they were figuring out what they were going to do by exploring the United States, Zeppelin took his staff and roamed around on the Mississippi, found Steiner in St. Paul, Minnesota, and they went up. And Steiner wanted to know, how do you direct your balloon? Can that be done? And Steiner told him he'd been thinking about that for some time. And the only way he could figure out how to do it was create a balloon in sections, create a aerodynamic feature, and then somehow propel that along. And Steiner wrote that to his father, this really great idea, never forgot that. And then indeed, when engines were created and you could actually propel yourself forward, he then went back to that idea and created his line of Zeppelins before World War I. So the seeds of these kind of flights germinate in really, you never know where they're going to come up again. And now we're flying on Mars. What a fantastic concept on another planet.
And balloons aren't useless here. We can explore other worlds with balloons as well. And of
Correct.
course, they're different designs, but so was the Zeppelin versus a hot air balloon. You know, Zeppelin was this hydrogen-filled, very dangerous, very dangerous airship, but
Right.
it was still an offshoot, a technological offshoot from those original early balloons. Now, when did ballooning start? I mean, when was the first person that said, I am going to fill that thing with hot air and get in it and float?
Well,
you know, Lord knows
yeah.
how high.
Yeah, that was in the, we'll say, late 1700s in France. Montgolfier really was the first one to think of the hot air balloon. You know, hot air rises. If we capture that in a nice thin bag of sorts, can we loft it? And indeed, that was the start of that whole concept. In fact, I think Ben Franklin, who was over in France at the time, had an opportunity to see ballooning. But indeed, it wasn't until the U.S. Civil War that we really started to think about it as an important perspective to use to be able to gather military intelligence. Fast forward to the space era, even the USSR, when they were going to Venus, we actually had several balloons that they launched in the atmosphere of Venus. And they operated for 20, 30 minutes until, they couldn't be seen anymore. And then that information was radioed back. And so the concept of using balloons is still very viable, not only at Venus, probably not so at Mars. We're going to stick with the powered flight, but places like Titan, which has a significant atmosphere. It has twice the amount of atmospheric pressure as we do here on Earth. It's dominated by nitrogen, but it's also very cold and has methane and other kinds of trace gases that are in the atmosphere, but still very navigable with balloons. So that's an idea that's been talked about.
So this probably has to do with atmospheric pressure, right? Whether you use a balloon or a copter. So in the rarefied atmosphere of Mars, a copter is a better solution as opposed to something thick like Titan or, say, Jupiter. A balloon is more suitable, right?
Indeed. It's all about those kind of dynamics. I mean, in reality, when the concept of ingenuity really started, there were many engineers, even at JPL, that said, we don't think this is going to work. And so, indeed, JPL started with an internal investment and developed that idea. They proposed it when we had a call for instruments for Perseverance. And indeed, we finally accepted their proposal and basically stated, this is a technology demonstration. When we launch, you better be ready or you're not going. Okay, we're not waiting for you. And indeed, they proved the technology out in a very methodical, steady way, tested it in chambers that had the approximate pressure of the surface of Mars with carbon dioxide. And so indeed, they got a ride. And indeed, it's worked out wonderfully. We're so delighted.
Indeed. Ingenuity has worked, which it really was a technology demonstration first and foremost anyway, and technology demonstrated, right? this
right.
worked. Now, what have we learned from the flight as far as a nuts and bolts perspective? What have we learned about flying around on Mars with a copter?
Oh, a number of things. First of all, to be able to make it work, it had to be light. And so they perfected the concept of how light. The copter only weighs about 4 pounds, okay? the demonstration that we've done with it, and we've had 9 flights now, 9 successful flights, just finished the 9th one, shows that, scaling wise, we could probably increase the mass of the copter maybe into the 30-pound area. Now, this is tremendously exciting, okay? So as a technology demonstration, it can feed forward into some new concepts in terms of flying. If we're going to fly a 30 to 40-pound helicopter, okay, successfully, we now know that we can add to it a significant set of instruments. Things like methane sniffers. We know that Mars is emitting methane through its surface. Curiosity has been measuring methane all the time above its threshold, and then sometimes it gets spikes of methane. So some really exciting results from that. But we also think there's areas where there's more methane that's being liberated through the surface than others. It would be great to be able to fly back and forth like drones do in certain patterns, and scout out a large region and map where these methane vents might be. And this then would focus our surface mission to be able to go down and really gather enough methane for us to be able to determine through isotopic measurements whether it's biologically generated or abiotically generated. And that's just one of a whole series of other things that these helicopters could do.
I will get to the question of methane in a different context in a bit. But now with Mars, what about the science of the copter? What have we learned scientifically from the flights?
So up until the 9th flight, we were performing a variety of test flights. The ability to go up and then come down and set it down on the right spot, okay? The ability to translate, come back to that spot, the ability to jump to a new airfield, all right? And then, of course, testing the limits of how long can you fly and what distance can you do and how fast can you go. Now, all those tests have been tremendously successful. And we now moved into the 9th flight into what I would call its really first opportunity to do science in conjunction with Perseverance. The area that Perseverance and Ingenuity is located is below the delta. This area where a river flowed into the crater, sediments dropped out because the crater was full of water, actually from the ancient ocean that poured in, and then that still water made those sediments to fall out. And so sediments over time in this river entry into the crater has built up to about 65 meters in depth. And so we're at the crater floor. We're just outside of that. And so we want to learn all kinds of things about the crater floor. It has some difficult places to get to, places where Perseverance would have a very difficult time to get into, to examine this area more thoroughly. So we're going to send the helicopter. So we indeed did. We sent it over a very rough area. And what we were looking for from that perspective is there places where not only Perseverance could go if it needed to, but whether there were some interesting spots that we hadn't really realized that we would like to go and test. So the first phase of the Perseverance science is really to explore that crater floor. Perseverance is being helped by Ingenuity, who is looking around and helping chart that next series of measurements that they'll make.
So it's a dual mission in that you've got a scout and a scientist, a robotic geologist. Now, what is the future of flight on Mars? Now, can you envision a fleet of sort of copters in sort of the herald before actual humans set foot on Mars? Do you think that this is going to be a crucial technology that's being demonstrated right now that will help us to successfully put human feet on Mars?
I really do. There'll be a number of scientists and groups that will hold on to this technology and begin to think about what are the things that it could do. Now, not only can it, as I mentioned earlier, scout areas looking for methane vents, But another aspect that it could do could really help human exploration. We have found there are an extensive network of lava tubes. Mars actually was quite volcanic. There's a region on Mars where Olympus Mounds, which is just the ultimately huge volcanic dome, which is so big that if it came to the United States, it'd cover the state of Missouri. I mean, it's that big. And many other domes that are smaller near there. And so that's all been fed by lava tubes. They now have indeed cooled off. The tubes then are vacant. Some of them have collapsed roofs. This would enable a helicopter to fly into a lava tube. Now, that lava tube, we think, is at a constant temperature. Now, when you think about living and working on Mars, where the temperature changes about 170 degrees Fahrenheit every day, having the ability to go to a shelter that it is at a steady temperature, for which then the amount of energy you need to get it up to a livable temperature is known and can be done, and can be indeed reduce your risk of having huge swings in the power systems. So perhaps these lava tubes could be a really good harbor for initial humans to live in. From a scientific point of view, we want to know not only the temperature and pressure inside these lava tubes, whether there's also the water that is accumulated. And perhaps in ice form, there may even have been a colony of microbes that could have gone into these lava tubes and lived, and perhaps there's some evidence of life in those. So it's really an exciting opportunity to explore in ways that we could never imagine before then. The ability to get into these huge lava tubes was quite daunting when you think about trying to have a rover and lower itself in, whereas you can just plop in, fly in, all right, explore around, and then come out. That's pretty sensational.
That is unbelievably cool. Now, let me ask you this. You got my imagination going.
Good.
So, okay, we got lava tubes underneath the surface of Mars, and I actually thought about those in a novel long ago. But the thing is that gets down into liquid water levels of Mars, right? So, I mean, you could have an aquifer and a spring inside of this thing that's, just pouring out and evaporating into the Martian atmosphere, whatever pressure is down there. That's on the table, right?
Well, that's a good question. It really depends upon the pressure and the temperature in these lava tubes. If it's a constant temperature, is above freezing, it probably is not, but okay, has to be that, and a pressure for which then the water can stay together and not sublimate, and it's probably not at that high enough pressure. But at one time, all those situations could have occurred, all right? Because Mars' surface pressure was much higher than it is today. So indeed, at one time, that may have been going on inside a lava tube. And so the only way to find out is to go on in and explore it. Do the spelunking we need to do, right?
The spelunking Mars drone. I can't think of a more amazing idea. Now,
yeah, I think NASA will come up with what that acronym is. Whatever spelunk is, we can figure out a good name for it.
Well, spelunk. Just come up with the different scientific things to fit the word spelunk.
That's right.
Now, this also seems to offer two other opportunities, because if you have a lava tube that you can found a semi-permanent or permanent human colony in, that gives them one way or another access to water, perhaps. Yep. And number two, protection from radiation, because magnetospheres. So this seems like the ideal place to put a human outpost on Mars, right? Correct.
I mean, it has features that are very appealing. So I would say at the moment, we haven't made decisions in that respect. So everything is on the table. So this next decade to 2 decades, in particular, is the perfect time for us to figure out what these forward-thinking missions should be that not only do an enormous amount of fabulous science, as I mentioned, by looking for life inside a lava tube, but also scout out areas where humans could occupy in a safe and protected way. And so indeed, lava tubes are a possibility. We'll have to see.
This is sort of poetic if you think about it, because some groups of humans on Earth in a very, very distant past used caves and lived in them, at least at the mouths, and then they went deeper into them and painted them with their technology. So here we are, history repeating itself with humans going and living in a lava tube cave on Mars, and perhaps somebody will paint something on a wall. History does indeed repeat itself, don't you think?
Well, John, I think you're leaning forward on that one because a complex life on Earth didn't arise for several billion years. So if there's any painting on the cave wall, it's the way the microbes have arranged themselves. But that indeed would be a fabulous discovery, And we're not saying that's possible, but we would like to investigate it.
Microbe residue paintings on a lava tube on Mars. How do you even digest that? Now,
it can't get better than that.
It can't get better than that. Now, how about Percy? How is the rover doing, and what have we learned so far there?
Well, since it landed on the 18th of February, of course, it goes through a variety of processes. And the first one is a liveness test, and then a thorough examination of the health of the rover and all the experiments. And then each of the experiments takes some basic data. And then all that is brought back and analyzed. Now, that typically takes at least a month to do. And I'm happy to say that's all been accomplished. So we have indeed made progress of seeing how healthy the rover is. It's very healthy. It's just in perfect shape. Actually, the way NASA likes to call it is it's in a nominal condition. It's the most understated, important word about an operational capability in space I've ever heard. But if it's nominal, to me, that means it's ready to go. And so indeed it is not only worked with ingenuity by dropping it off and then participating in those tests. We need the rover because the rover is what is the surface feature that actually communicates with ingenuity. So ingenuity has to go through the rover to speak to the ground. All right. So therefore everything that ingenuity's been doing in its 30-day plus tests required Perseverance to do it. But Perseverance is starting to do the science now. It's charting a course. It's made some initial measurements. It has a laser where it zaps these rocks and then can look at how these rocks heat up and get an idea of their composition. And indeed, in this area where Percy is at, there's a lot of basalts. Now, that means these are volcanic rocks that have been melted, thrown out of a volcanic area, or perhaps ended up in this river that then flowed for hundreds of miles and then deposited these rocks at the end of the delta, spewed out all over the place at the crater floor where we're at. So that's really exciting. So we want to figure out what these rocks are made of so that we can figure out perhaps where they came from. And that means there is a possibility that there's some volcanic activity in the past close to where this river was. That's exciting. And now, indeed, having ingenuity scout out some places has enabled the science team to figure out the next set of measurements they want to make. But they will stay down in exploring the crater floor for many months before they start taking the trek onto the delta. Now, one of the experiments that I'm excited about all of them, but one that's really unique that can explore the delta, in my opinion, is the radar. We have a ground-penetrating radar developed in Norway. It's a fabulous instrument that then can really get us the stratigraphy of this delta. In other words, there could have been huge flows at one time, and then droughts, and then bigger flows, and deposits, more and more deposits in certain areas than in others. And so we might be able to get an idea as to seasonally how this delta was deposited over time. So we're really in for a treat, and we're all set up ready to go. I think in the cratered floor area where Perseverance is at, they'll be planning on creating their first couple samples coming up. So that's the next big step for them.
Now, this is interesting because we're talking about sedimentary rock. We're getting closer and closer to paleontology. And this has happened before. You remember the blueberries and past Mars rovers and landing right literally in front, like 20 feet away from a sedimentary rock deposit on Mars. Now, this is really unusual and very Earth-like, this situation, because that implies water in and of itself, right? So what can we do learning from the layers of rock that the ground penetrating radar may be able to see and we may be able to characterize? Does this give us a sort of roadmap on where to look for fossils of life on Mars, should it have ever existed?
Very interesting question, because one of the top things that Perseverance is designed to do is to core rock. All right. So indeed, the stratigraphy, the layering, may tell us there's certain layers that actually become exposed due to other processes, maybe wind processes, aeolian processes that have then gotten to a particular layer that we could get into. We also know that when you look at the delta, there are some impact craters there, which also then open up lower layers for us to be able to potentially go in and sample. And indeed, that then takes us back in time. The type of samples that we create are indeed cores. Let's see, I have what a core looks like right here. When I was out at JPL looking at the engineering unit several years ago, I had them core a piece of granite, and here it is that we use in the engineering unit. So it's like a piece of chalk on a chalkboard. And for those kids that may be listening to your podcast and don't have any idea what I'm talking about, it's the size of a large Crayola crayon. So this then ends up being put in a sleeve, a metal sleeve like this, and then capped and sealed up, and then it will be deposited on the ground for later pickup. Okay, that'll be the next set of missions. Now, what do we expect to find in here? Well, indeed, the rock record on Mars, just like the rock record here on Earth, tells us how Mars has evolved. What has been the interaction between air, the atmosphere, the water, and the land over time. We also know here on Earth, when we've done these kind of things, that there are about 5,000 minerals. In other words, how material clumps together to create a lattice that forms a rock. And that unique configuration we call a mineral. Out of that 5,000 minerals here on Earth, 300 of them or more on that order can only be made by life. So by bringing back the rock record, we're going to get a much more extensive idea as to the mineralogy of Mars over time, well into the past. And the hope is we may be able to find minerals that indeed could only be made by life, and that would be indeed the extinct life that may have been on the surface of Mars. So what we have to do to be able to better our chances of being able to make those kind of discoveries in the rock record is to really figure out where the best places to go to get the samples, because we only have a certain number of samples. Now we have more than 40 sample tubes on board of Perseverance. And so over time, over the next several years, we're going to be making those choices, coring those rocks, putting those samples in the protective sleeves, and then laying them on the surface for later pickup. So we have to be very judicious about doing that. But we have several years to do that before we'll launch the next set of missions that will go and pick up the samples and bring them over to a Mars ascent vehicle that then will blast off the surface of Mars, another first, okay, and then put them into orbit, for which then we'll have another satellite retrieve that set of samples and bring them back to Earth. So it's an involved process, but a really exciting one.
Regarding geology and Mars and taking samples like that, is there, what is the selection process when you're looking at rocks? Do you say, well, that's just a piece of basalt. We know what volcanic rock looks like. We have already essentially have samples because there are Martian meteorites that are basaltic. So are you being choosy and sort of saying, well, we only have this many chances. We're only going to take samples from the really most interesting specimens that we see on the surface? Is that sort of skewed that way, or are you just taking a random sampling?
Oh no. We're going to be very careful, very judicious about each sample that we take. This is why we have a science team. And the science team has several hundred scientists. All right. And they're going to be arguing. And it's going to be exciting just to listen in on some of these. Do we cut the rock here or there, or what are we going to do? In fact, members of the science team have gotten together and have gone to places here on Earth. Some of the oldest rocks here on Earth in Australia, looking for certain patterns in the rock face that might tell us or give away some of the important parts of how that rock was developed. And in that, they found these fossilized stromatolites. All right. And so they have certain patterns where microbial mats just build up over time in an area of the Earth that was like a pondish, shoreline area. In fact, stromatolites are still there in Australia. They're probably the oldest type of life that we have here on Earth is these microbial mats. So being able to recognize them in the rock record will be an enormous step forward in trying to understand if Mars was like Earth at the same time that Earth was creating an environment for which these stromatolites occurred. All right. So these are going to be extremely important science meetings, and a lot of arguments are going to be presented, pros and cons for each one of the samples they're going to take.
Now let's change focus from looking at our solar system to looking much further. James Webb, the
Yes.
James Webb Space Telescope, the long-awaited, long-delayed James Webb. How is it looking now? Does it look like we're actually going to be able to get it launched and operational in short order finally?
Oh, absolutely. We're coming up to what's called a Preship review. So Webb has passed all its tests. It's in great shape. We're going to be looking at literally after the review, boxing it up and then sending it to Corona, where it will be launched. It will be launched by the European Space Agency on an Ariane 5. Now, what's exciting about that is indeed it takes a couple months for once the mission arrives for it to go through what we call payload processing and be able to be ready. So they have to, construct the rocket. They have to get the payload inside a fairing. They have to mount the fairing on top of the rocket. They got to get the rocket in position. And that's just the very top part of all the tests and things they have to do. And that takes a couple months. So indeed, the concept is that we'll ship it. 2 months later, it will be then ready to launch. So we don't believe it will be launched prior to the end of October. In fact, we're looking now into dates in November. But indeed, that whole launch activity is managed by the European Space Agency. And they have their own schedule, where they'll be launching things and testing things. And we want those to be successful. And we want to be them that next successful mission before the end of the year. So I think we're moving in a really good way. So it's going to happen. It's going to happen.
Well, there's no question that the Ariane launch system is a venerable, reliable way of putting it up there. And once we get it up there, of course, there's going to have to be all kinds of more, testing and make sure all the systems are working and everything before true science first light happens. But once that happens, once James Webb is online and ready for science, what's on the agenda? What's first on the agenda to study?
Well, indeed, what's first about Webb is getting it to its place. And there's a certain timeline. So after it's launched, it will actually take a couple weeks to put it into a very special place we call L2. And this is a Lagrangian point. It's in the magnetotail of the Earth, and it's about 235 Earth radii away from the Earth, okay? So it's very far away, more than a 1.5 million kilometers. Now, in this position, it enables us then to be far enough away from the Earth so we don't have a lot of Earth interference, but close enough to Earth that we can track it and that it will stay with Earth as we go around the sun. Now, this requires, after launch, for it to unfurl, for it to, spread the mirror. Everything is like origami, where it's now all closed up and in a tight position. And all that will have to be deployed. The mirror, for instance, is huge. It's 21 feet in diameter, okay? This is more than 2.5 times the size of a Hubble as a mirror. And then, of course, in the infrared, we have to keep it cold. And that's another reason why we want to go to L2, is it's a cold place. There's not a lot of heat that comes from the reflected light of the Earth shining on it. And that's also why we want it on the night side of the Earth, to get away from any reflected light from the Earth. So in that position, then, we'll have a shield that will be the size of a tennis court. That'll have to be deployed. And then we'll be able to look out with the fabulous mirror over a wavelength regime that starts in the visible and goes right into the infrared, and look back in time. It's really designed to look back in time, where we can see the first galaxy starting to be formed. Now, that's really exciting. The concept is, the Big Bang occurred, material was then hydrogen and helium with a little bit of lithium that then coalesced and started stars, and then multiple stars then began to be gravitationally interacting, creating galaxies. So what did those galaxies look like? Did they form as ellipticals, or were there spirals right off the bat? What kind of structures do we expect to see those first galaxies? So it has a fundamental role in looking at how the early universe started to be put together to where we see it today. But it has other fantastic things that it will do. Because it observes in the infrared, it can look out and look at Kuiper belt objects. We'll see the asteroid belt. It can see things that grab heat from the sun and radiate that heat in the infrared. And so those objects will be very bright. So we're expecting all kinds of discoveries, not only in astronomy, but also in our own solar system. And if we're lucky, we'll be able to actually look at some atmospheres of planets that are orbiting other stars. And so all that is being planned right now, getting ready for James Webb to come online.
Now, exoplanet atmospheres, we'll get to that in a moment, but I wanted to ask you a question first, a little bit more nuts and bolts question that's originally was posted by one of our supporters on Patreon. And it's an interesting idea. Now, we have bigger and bigger rocket systems coming online, whether it's SpaceX, Blue Origin, or the SLS. We can launch bigger payloads now. What implications does that have on what we can do with robotic science missions in the solar system? I mean, we could launch a lot more payload, just like with the copter being able to scale that up. Our rockets are being scaled up. So, what do you envision our abilities to explore the solar system robotically? How is this going to benefit from all these new systems?
Yeah, you've touched on a really important point, and that is the more capable the rockets we have. In other words, their capability can be thought of in a couple ways. One, they can lift more mass into orbit or out into the solar system, or they can lift a very light mass but end up going faster. So we can trade these concepts off. Do we want to go fast? Do we want to lift a lot? And we want to get things in different locations. So what it does is it opens up the space for scientists to think about how their mission could be constructed that would take advantage of these more massive rocket capabilities. Now, the concept of going fast, why would we want to go fast? Well, all you have to do is think about where the Voyagers are. We have two spacecraft, Voyager 1 and Voyager 2, that have gone through what we call the heliopause. And this is the extent of the sun's magnetic field then runs into the winds of other stars. It's blown back and shaped by that wind. And the Voyagers have punched right through that area. And now those Voyagers are really tasting the winds of other stars, okay? But unfortunately, the Voyagers weren't designed to do that. And many of their experiments are no longer operating, those that would be needed to make really important discoveries about what's happening in interstellar space and the winds from these other stars. So indeed, the concept of creating a smaller spacecraft and using a larger vehicle to give it a huge boost in velocity to then get it out to the heliopause much quicker than the Voyagers do are those kind of missions that are currently being planned and talked about. This mission is called Interstellar Probe. But indeed, the larger launch vehicles will be able to take more mass, such as, giving an example, the NASA's Space Launch System, the SLS, is coming online. It's being assembled right now in the vertical assembly building at Kennedy Space Center. I mean, this launch vehicle is 10% more powerful than the Saturn V's we used to launch. And it has the ability, of course, to take humans, in addition to a cargo, to the moon and then onward towards Mars. So it's not only the robotic capability that we're talking about, but it aids significantly in our plans to support human exploration.
And indeed, SLS is specifically for that. That's its first mission. Now, I want to ask you, though, this changes the sort of map as far as what we can do with the solar system. Now, you mentioned Voyager. Voyager 2 and Voyager 1. These were launched on an opportunity, a chance alignment of the planets so that we could just sort of slingshot around and do the grand tour.
Right.
But when you have more powerful rockets, like, better than Saturn V, a lot more comes onto your plate. You can more directly explore the solar system. So does this factor in with NASA's future planning on missions? Because now outer solar system objects suddenly are a little bit easier to get to, right?
Oh, absolutely. When I was head of planetary from 2006 to 2018, before I became the chief scientist, one of the big studies I had tasked JPL to do and others was to look at how we could get out to Uranus and Neptune and go quickly and be able to study those two ice giant planets in modern ways. I mean, we've only visited them with Voyager 2, only one spacecraft. And yet we know so little about them, we need to go back. And so indeed, enhancements in the launch vehicle do indeed cut down on the time it takes to get there.
Now, in regards to one particular system, Saturn, now, of course, we have Titan, which is unbelievably amazing, but we've actually landed on Titan. We've done a little bit of exploration, but we got another one. We have Enceladus, and just yesterday, Enceladus seems to be emitting methane, which could be a biosignature. It could be a signature of life on that little moon. So is this now moving onto NASA's plate, this idea of not just looking at Europa, but also Enceladus and seeing what's going on there with these two similar oceanic ice shell moons?
Right. Indeed, we've always been excited about Enceladus ever since we found the plumes. And we call them plumes, but in reality, when we look at it in backlight, they're literally walls of water that come spewing out of these cracks in the southern hemisphere on this tiny moon, which is only about 300 kilometers in size. And it's close enough to Saturn, though, that Saturn is squeezing it. And so as it moves in its elliptical orbit, it gets squeezed when it's close, and it opens up the cracks when it's further away in its orbit, allowing more water to pour out. Now, we have flown through those plumes several times, all right? And so this is data that's in the archive that is constantly available and available to analyze and reanalyze. Now, we've known that in these plumes are organic material, organic compounds, whether they are biological or not has always been the question. And Cassini couldn't tell the difference on that. It was never designed to be able to tease out whether there was life there or not. So consequently, in the reanalysis of the data, we have to bring other techniques to determine if there's a portion of the methane that could be generated biologically and what that portion would be, making certain assumptions about the hydrothermal vents that we know are at the bottom of the ocean in Enceladus. And so that's what the paper is all about. Now, unfortunately, we have no real idea of how much initial methane was in the body when it was created, and it's being liberated at this time with the methane that's being generated by these hydrothermal vents. You can make methane abiotically. It requires a hot source, potentially magma, and the right minerals, such as olivine, and water. And that interaction indeed can generate methane. And so that methane would be abiotically generated. So is there residual methane that it was created with? Is there methane that's being produced biologically in addition to the methane produced abiotically? And that's what the paper talked about. Great set of research, but not definitive. It doesn't tell us there's life there, but it gives us that hint as to the kind of experiments and what we need to do when we go back. Now, Enceladus is an opportunity that can be accomplished through a variety of future missions that could be proposed in some of our calls, like Discovery. And in fact, it's also been a target in our larger missions that we allow the community propose called New Frontiers. So I'm thinking there'll be other scientists that are on the same wavelength as you are, John, and that we got to go back to Enceladus. But right now, of course, we're developing the Europa Clipper mission that's designed to go to Europa and really interrogate that, because that moon is huge. It's not small like Enceladus. It's the size of our own moon, just a little smaller. And it has, we know, huge cracks for which water has communicated to the surface because there's hardly any craters on the surface. So all those craters that occurred over time have been eradicated by the water communicating to the surface. So it's actually still a very active body. We even see indications where one ice sheet is moving underneath another, just like plate tectonics here. We know that it has an enormous ocean that perhaps is in some places more than 100 kilometers in depth. And we believe strongly that there'll be hydrothermal vents at the bottom of that ocean. And therefore, it has all the right conditions for life to have perhaps started there too. And the Europa Clipper will give us a really good idea as to that potential for life.
Now, this is a shot in the dark, just something that just occurred to me.
Okay.
If we're looking at methane, and I don't know if anybody's has looked to see if Europa is exhibiting methane or not, or if we even have the capability, but we have it with Enceladus. Now, here on Earth, we have clathrates where methane can actually form as an ice. Are the pressures and temperatures that are predicted at a place like Enceladus in that ocean, does this open up the possibility of geologic methane being stored on the ocean floor of a place like Enceladus and eventually being released, creating that signature like it happens here on Earth?
Indeed, we think the same physical processes are viable. And so that's why, because that's an unknown, is whether that's really going on at the bottom of the ocean. We think it does have that capability. So if it had that initial distribution of methane, could it be maintained by, indeed, this process you call clathrates? And we think that's viable. Yeah, why not?
Interesting. Now, one more body in the solar system we have to discuss here in regards to this biosignatures. Okay. Venus and phosphine and all the other little tidbits and hints that maybe something's going on there in the upper atmosphere, or maybe not. What are the plans on NASA's plate, if any, to look into that? Are we going to go to Venus anytime soon?
Well, yeah, indeed. We just selected 2 spectacular Venus missions in the Discovery program. The first one is called Da Vinci Plus. This is the one that relates to really teasing out the phosphine question. Phosphine is 3 atoms of phosphorus that are connected together, okay? And here on Earth, there is some type of biology, particularly in bogs, that generate phosphine. So the concept is if we see a lot of phosphine, particularly at high altitudes in Venus, could that be generated by microbes, special microbes that then this would be part of the metabolic system. That concept then was pushed further by some observations that came out initially. And then those have not been reproduced. In fact, there's some real problems with the analysis that was created. That happens with all the types of data that NASA creates, the National Science Foundation, and any of these scientific organizations. You have to be able to calibrate it. You have to be able to ensure you understand all levels of contamination and then eliminate that. And so when that announcement came out, indeed, it was very exciting, but further scientific work puts doubt in our minds as to whether there's any significant phosphine in the high clouds of Venus. Now, Da Vinci Plus will be able to, as it goes through this region, make many measurements looking for phosphine. Now, it's not the only thing it's going to be looking at. It's going to be looking at the noble gases, and it'll be looking at, as it goes through this middle atmosphere, much more of the composition, its temperature and its pressure, as this probe then goes all the way down to the surface. And so it's really our first extensive chemical analysis of the atmosphere and the dynamics of the atmosphere from being in the atmosphere. All right, and so that's a really exciting mission. The other Venus mission that we selected is called Veritas, and Veritas has a number of spectacular capabilities. One of which is it has a cloud-penetrating radar, a very high-resolution radar that then will give us the surface features underneath this hugely thick atmosphere and intense heat that's on the surface. Now, we've done this before, but at a very low resolution. Veritas is designed to make high-resolution measurements that will enable us, I think, to be able to determine conclusively whether Venus had plate tectonics or not early on in its history. And of course, we want to know if there's active volcanoes. We think there are. There are here on Earth still active volcanoes. In fact, there's 3 spectacular volcanoes going on right now on Earth. And we think that Venus is still very volcanically active. Now, I will mention that indeed volcanoes actually here on Earth are known to produce phosphine. So indeed, just because we observe phosphine, if we do with Da Vinci in the atmosphere, doesn't mean it's biologically generated. It could still be generated by these volcanoes abiotically. But that's important measurement to make anyway, because we do want to understand that environment and how it has evolved over time.
Now, I have 2 final questions for you, but before we get to that, I wanted to tell everybody about your podcast, Gravity Assist. Tell us about your podcast, Jim.
Well, indeed, this is my 5th year. Gravity Assist has been just a fun thing for me to do. I really enjoy talking to my science colleagues. And early on, I thought, hey, it would be great if we could just create a podcast out of it. I want to learn what they know. They're doing some spectacular science, things that won't be in textbooks for a decade or more sometimes. And we can talk about it that I think makes it very accessible to many people in the public that would like to know what the heck is NASA doing? What are the exciting things that we find? But the concept of Gravity Assist has another angle to it, and that is every one of our scientists that get into this field, we weren't born with the idea, oh, I'm going to become a scientist. We actually run across that in our life. There's something that happens, a person, place, or thing that gets us so excited about what we want to become in terms of that scientist. It changes our direction and accelerates us forward to become the scientist or engineer that we are today. And that process is very identical to what spacecraft do when they pass by a planet. They change their direction and they get accelerated to the target. And that process is called a gravity assist. So I always love to ask whoever I interview what their gravity assist was. And it's all over the place, which is really fun to listen to.
Now, there'll be a link in the description below to the Gravity Assist podcast. And I recommend it because if you like this show and you like what we do here, you're probably going to like Jim's show too. Now, Jim, James Webb Space Telescope and characterizing exoplanet atmospheres for biosignatures. We're going to be able to do a little bit of that. We need a lot more instrumentation, but James Webb is the first step. Give us the lay of the land on that.
Well, you know, as Kepler proved that there's an enormous number of planets out there. In fact, after the end of the Kepler mission, we realized statistically there are more planets in our galaxy than there are stars. Okay, and so these planets come in all sizes. Some are Earth size, some are less, some are Jupiter size, some are less. And in fact, we found a new category of planets called super Earths, a type of planet we don't even have in our solar system. And it turns out to be the most populous planet that we expect to see around other stars. And these are typically up to twice the size of the Earth, but maybe have as much as 10 times the mass of the Earth. And they may have extensive atmospheres, and they may have extensive oceans and atmospheres. And it's that class of planets we think that James Webb will be able to look at their atmospheres. Now, what's really exciting about that is the atmospheres can tell us a lot about conditions on the planet. The temperature, the pressure, let alone the composition, and give us an idea of whether that environment can actually be what we call habitable. You know, if life like us was there, could we live and survive in that kind of environment? That's what the concept of habitability. And mostly it is all about whether it has the right conditions where water, liquid water, could exist. because we think liquid water is really critical. It certainly is for life like us. And there might be other life that uses other liquid. But right now, if we can find a massive evidence for water in some of these planets, that could give us the indication that they are habitable environments, and we need to explore them further. Now, out of the thousands of exoplanets that we have found, we've only been able to measure about 50 atmospheres from the details of getting their spectra. So we have just started that process, and they have to be close to us, and they have to have certain characteristics for us to be able to even try to see them. But with James Webb, it now opens up a larger set of planets for us to interrogate their atmospheres. So we're going to see, I think, some really big steps in this particular area, and in particular for atmospheres of super Earths on up to Jupiter-sized planets.
And that leads us to the final question of the interview.
All right.
Technosignatures.
Yeah.
And now we've covered biosignatures. Now let's talk about technosignatures, looking for advanced alien civilizations distantly out there. What's on the table for that?
Well, right now, about 2 years ago, we have to extract the COVID year that we just went through, we had a workshop on, well, what would be the technology signatures that would indicate advanced life, all right? And so we had a group of scientists come in. They did a fabulous job trying to identify things that we should be on the lookout for that could identify or really give us the indication that there's advanced life, intelligent life on these planets. So what would that be? Well, one example would be in their atmospheres, if we can find certain chemicals for which they don't occur naturally, that have to be made, that's an indication of intelligence. Another technosignature would be perhaps structures, large structures that are built in space, perhaps to capture sunlight and then direct it to the planet, perhaps screening sunlight that enables some planets to maintain a certain steady solar input that allows indeed that planet to stay within a habitable zone. Another technosignature could be as we look at a planet before it transits the sun. In other words, before it moves in between the star and us as observers, when we're only looking at the night side of the planet, are there artificial light there? Do we see emissions that can only be created not by nature, but by intelligent life? And so these are just a few of the examples of what we call technosignatures. And so Webb will actually be one of our first examples by teasing out in these atmosphere whether there are certain chemicals that aren't made naturally or not. But other plans are indeed to get higher resolution instruments to really interrogate these planets on a much bigger, in a much bigger way. Now, some of those ideas involve bigger telescopes than Webb. And so these are big dreams. Our scientists always dream big. And there's a reason for that, the reason that we need these big telescopes. But our purpose right now is to make sure Webb is successful. We get it on orbit, we get it unfurled, and we start making these unbelievable, spectacular measurements that will lead us to the next set of questions about our universe.
And to end this on this note, now, okay, we have all these hints from multiple bodies, ice shelf, moons, Venus, Mars. We have all these hints that maybe there's more life in the solar system than simply us. Maybe it's related, maybe panspermia happens, something like that. Or maybe they represent, if they exist, independent occurrences of life in the solar system, independent, completely separate from Earth. Should that be the case, and we find it, NASA goes and studies Europa and finds microbes living in the water. Mm-hmm. Would that indicate to you, and to everybody for that matter, that this galaxy absolutely teems with life and maybe the occasional civilization, and maybe this isn't all that hard?
Yeah, I think so. I think it's a perfect demonstration that life may be all over the place. Why it's so hard to do, how come we don't know that right now? Is because we don't know everything about how life can evolve and how it can change and in what forms it can take. So we had to start out with some basic definitions and build from that. Also, when we look out into our solar system, we are in the habitable zone around our star. Okay, Venus isn't. Okay, Mars isn't. All right, even though they were blue planets at one time, that's because they had significant atmospheres that provided them the heat that they needed to maintain liquid water on its surface. That turns out to be much easier for Venus. And in fact, Venus may, with its runaway greenhouse, have been habitable for more than a few billion years. So Venus might be that first habitable planet in our solar system. And so when we think about life, we have to think about the evolution of these solar system bodies and what's happened to them over time, where life could have come and gone on certain objects. And here we are in an instant of time trying to figure out not only what's happening around us at this instant, but also what's happened in the past and what could happen in the future. We are the first species on this planet that can do these kind of thinking and look for these kind of signatures and understand that there may be other types of life beyond Earth. And so we're struggling now to be able to effectively figure out what's happened in the past and then using that information to determine what will happen to us into the future.
Amazing. Jim, thanks for joining us today, joining us again, and I hope you'll do it again in the future. And my best wishes and best of luck to you and everybody at NASA in exploring this stuff. It's hard to overstate how exciting these times are.
Well, thank you very much, John.
Anna, I have a surprise for you.
Is it another rock, John? A rock?
No, introducing Annabot.
So I am Anna.
Oh, well, that didn't work.
Oh, points for effort, though.
Indeed. So, what's for dinner?
Spaghetti, John.